All right, so here we go. Oxidation reduction is the last type of reaction in chapter 4. People usually just refer to it as redox. I don't know, did anybody get to it in Chem 1? We always have lofty goals in Chem 1 of actually getting to redox, and then it never happens. At least it did for me last year. So oxidation reduction is all about an electron transfer. Okay? And oxidation is the loss of electrons. Reduction is the gain of electrons. Okay, there's an electron transfer that's taking place here. There's one species that's going to get oxidized, it loses electrons. There's another species that gets reduced by gaining electrons. What it forces us to do is become electron counters. We're going to have some sort of system to track the electron flow. Okay? So the first part of redox is to figure out, well, how are we going to do that process? And so what people invented was the concept of oxidation state. And you already have been using it. So when you say, oh, sodium, for instance, is a group 1 metal, what charge does it have as an ion? And you say, oh yeah, group 1's +1. That +1 is its oxidation state. Okay? So elements, just in their natural state, have an oxidation state of 0. If you have an element with a charge, like sodium +1 or oxygen -2, that's the ion's charge is the oxidation state. So, but where it gets a little bit more confusing is, what if you have a polyatomic ion, or what if you have a compound that's a group of elements together? Okay, then you got to try to sort out what oxidation state each item has. And the good news is we get a lot of mileage out of 2 simple facts. Right? Oxygen, when it's an ion, or even if it's in a compound, we treat its oxidation state as -2. I mean, that's true 99.9% of the time. Right? And the other thing you can get a lot of mileage out of is hydrogen being a +1. So let me do some examples, and then I think you'll see what I'm talking about. Okay, so if we started really easy, if we started with the element nitrogen, let's say, well, because it's the element, the oxidation state is 0. Elements are always zeros. Okay, but let's put nitrogen into something now. Let's say you had nitrogen and it was in the nitrate ion. Okay? And what we're trying to be able to do is assign oxidation states to each individual element that's present. So you fall back on this, you say, well, oxygen's a -2. That's almost always true. And today's high-powered math, let's see if we can do it. If oxygen's -2, and there's 3 of them, that would give you a total of -6. The overall charge on the ion is -1. So nitrogen's oxidation state has to be such that when we add it with the -6, we'll end up with a -1 overall. Which means nitrogen must be in a +5 oxidation state. Now you can start to see differences in oxidation states if you think about different polyatomic ions. So, you know, that's the nitrate ion. Or what if you had the nitrite ion? Very similar, one less oxygen. Right, now you've got -4 for the oxygen. What does that leave for nitrogen now? Must be a +3, right? And so the difference between those two polyatomic ions is that nitrogen has a different oxidation state. Or, you know how we have that string of ions, hypochlorite, chlorite, chlorate, perchlorate? Take a wild guess what the difference is between all those ions. It's the oxidation state of chlorine. Right? So if you think about the chlorite, hypochlorite ion, what oxidation state do you think chlorine has? What do you think? So if it's +1, that works, because the oxygen we're treating is -2. So now if you start to go down the line here, so to speak, right, if you go to the chlorite ion, chlorine's oxidation state has now become +3, and you can just keep going right down the line. Because chlorate must be +5. Perchlorate, chlorine must be +7. And so, you know, if you look at the periodic table, that's why you start to see all these different oxidation states. Like sulfur, for instance, the table will say, well, it's ±2, 4, or 6. Because it depends what sulfur is combined with as to what its oxidation state is. You know, if we picked one more, for instance, what do you think is true about sulfur if it's in the sulfate ion? Sulfur would have to be a +6. What if it was a sulfite ion? Now it would be a +4. Remember this one? You don't see this ion is off. Remember thiosulfate? What does sulfur have to add up to in that case? So it would have to be a +2 to make the overall charge add up to be -2. Okay. So for any compound, ion, you name it, you can go through and you can figure out what the oxidation state is. And that's sort of the beginning skill level here, because we're going to use oxidation state and how it's changing to track our electron flow. Do you want to do anything more with this, or have I done enough that it seems reasonable? The only thing you have to watch out for with oxygen, when I say it's always -2, there is one polyatomic ion where oxygen has a different oxidation state. Right, O2 -2, remember which ion that is? Starts with a P. It's in a compound that you can buy at the drugstore used to clean out cuts. Peroxide, right? What's the oxidation state for oxygen atoms in a peroxide ion? Must be -1, right? So this is the only time you have to worry about oxygen not being a -2 if you happen to see the peroxide. Then it's a -1. Okay, so now the other thing you have to know then, before we really get into this, is if you're comparing something on the left side to the same item on the right side, you can spot if something's been oxidized if its oxidation state increases. Oxidation we recognize by an increase in oxidation state. Reduction would be the opposite. It would be a lowering of the oxidation state. And that's what kind of gets us into the ability then to track the electron flow. And we can look and see who increased, who went down. We can figure out how many electrons have been transferred. And that's really the heart and soul of a redox reaction. Okay. So you know how when you balance equations, normally we just do it by inspection? It's kind of guess and check. Right? You stick a coefficient in and you see, hey, does that balance this out? And you just kind of try different coefficients until you come upon a combination that balances the equation. Guess and check, or they call it balancing by inspection. In chapter 4 in our book, the only type of redox reactions they deal with are the easiest ones, the ones that you can balance by inspection. Okay? And they don't really get into the more difficult ones that we would really like to be able to do. They do it later in the book in chapter 18. So what I'm doing to balance these redox reactions is I'm really moving ahead in the book anyways to chapter 18. And usually I start out by showing everybody a real simple redox reaction. I'm going to have to do that one tomorrow. I'll show you a simple one tomorrow. But you could imagine something like this: aluminum metal reacting with iron 3 oxide. Let's see, I didn't have any of you guys in Chem 1. Any of you guys had Mr. Moore? Did you have Mr. Moore? Do you remember the thermite reaction in the spring?
Yeah.
Taking it outside?
Yeah, like the flower pot.
The flower pot? Yeah. Okay, this is the thermite reaction. It's hugely exothermic. It releases an incredible amount of heat energy. And it's also really a redox reaction because what the products end up being is aluminum oxide and iron. Now I would say this is a simple redox reaction. You could balance it by inspection. You could just sort of guess and check coefficients and you could balance this thing and you'd never even really know it was a redox reaction. Okay? But think about oxidation state for a minute. What would be the oxidation state of aluminum?
0.
This is a 0 because it's an element, right? How about on the other side, in aluminum oxide, aluminum has an oxidation state of +3, right? So can you see what's happened to the aluminum? It went from a 0 to a +3 oxidation state. So it must have been oxidized, right? If the oxidation state goes up, something's been oxidized. It means it's lost electrons. So aluminum is losing electrons. I wonder who's gaining them. Well, what do you think about iron in this compound? Going to be a +3, right? Because, you know, again, if you think of oxygen, right, it's -2. The iron's a +3. The oxygen's still a -2 over here. The oxygen hasn't changed oxidation state. But, of course, the iron metal on the other side, this is a 0. So you can see the iron is dropped in oxidation state.